It is traveling right now, faster than any human-made object in history. A machine the size of a small car, running on less electricity than a refrigerator bulb. Built with 1970s hardware and launched before most people alive today were born. It crossed the edge of the solar system over a decade ago, and what it found did not match a single major prediction. The magnetic field was wrong, the temperature was wrong, the boundary itself was wrong. 50 years of carefully built models were quietly dismantled by data arriving one tiny signal at a time. So what, exactly, did we get wrong about the edge of our own solar system? Subscribe so you never miss what we explore here. Let us begin. In the summer of 1977, 2 spacecraft were wheeled out onto launch pads in Florida, each one packed with scientific instruments, nuclear power generators, and a gold-plated record containing the sounds and images of a civilization that was, for the first time, sending objects far beyond the planetary neighborhood it had always called home. The people who designed and built those machines gave them a mission that nobody had ever attempted at this scale. Travel through the outer solar system, swing past the giant planets, gather everything the instruments could measure, and then keep going past the last planet, keep going past every boundary that anyone had ever drawn on a chart of the solar system. Keep going until the machines were so far from Earth that their signals, traveling at the speed of light, would take hours to arrive. The mission planners had high hopes. They expected perhaps 5 years of operation, maybe a decade if the spacecraft were extraordinarily lucky. They launched 2 identical machines to give themselves a backup, knowing that space could claim either one at any moment. Nearly 50 years later, both spacecraft are still transmitting. They have crossed the boundary of the solar system and are now moving through interstellar space, sending back data from a region no human instrument had ever sampled before. What they found there contradicted nearly every major prediction that scientists had made about what the edge of the solar system would look like. The story of those contradictions, and what they reveal about where the solar system actually sits in the galaxy, is one of the most significant and underappreciated chapters in the history of space exploration. It begins 12 years before the spacecraft launched, with a calculation that almost no one noticed. A scientist at NASA's Jet Propulsion Laboratory in Pasadena, California, was reviewing orbital mechanics in 1965 when he identified something that would change the trajectory of human exploration. He had noticed that the outer planets were drifting toward a rare alignment. Once every 176 years, Jupiter, Saturn, Uranus, and Neptune arrange themselves in a configuration that allows a spacecraft, launched at precisely the right moment, along precisely the right path, to visit all 4 of them in sequence, using the gravity of each planet to slingshot toward the next, without requiring additional propulsion for each leg of the trip. This technique, called gravity assist, had been understood theoretically for years. Applying it to an actual mission capable of visiting all 4 giant planets in a single flight was something new. The mathematics required extreme precision. The trajectory had to be threaded through each planetary encounter with accuracy measured in fractions of a degree, and an error at Jupiter would cascade through the subsequent encounters and miss every target. But the reward was enormous. Without gravity assists, reaching Neptune under the propulsion technology of the 1970s would take so long that any instruments along for the ride would be dead before they arrived. With 4 carefully orchestrated gravity assists, the entire outer solar system could be surveyed in roughly 12 years, while the spacecraft's nuclear power sources were still generating enough electricity to run the instruments. The window for this opportunity was narrow, and it was closing. To catch the alignment, NASA had to launch in 1977. The agency approved the mission formally in 1972, giving engineers 5 years to design and build machines that would have to work flawlessly across distances and time spans that dwarfed every previous spacecraft mission in history. The 2 spacecraft that emerged from those years of engineering were among the most sophisticated machines ever assembled to that point. Each one weighed roughly 1,800 pounds and measured about 10 feet across its main body, with a large parabolic dish antenna, nearly 12 feet in diameter, extending from the top for communicating with Earth. Each carried 11 scientific instruments selected to study different aspects of the planetary environments and the deep space through which the spacecraft would travel. Wide-angle and narrow-angle cameras were mounted on a movable platform that could be pointed in different directions during planetary flybys. A pair of spectrometers, one working in ultraviolet light, one in infrared, studied the chemistry and temperature of atmospheres and surfaces. A magnetometer extended on a boom far from the spacecraft body to measure magnetic fields without interference from the electrical currents running through the spacecraft itself. Multiple charged particle instruments counted and characterized the protons, electrons, and heavier ions flowing outward from the star at the center of the solar system. A plasma science instrument on Voyager 2 was designed to directly measure the solar wind's velocity, density, and temperature in real time. A plasma wave system on both spacecraft could detect oscillations in the surrounding ionized gas, revealing information about plasma density in a way that complemented but did not replace the plasma science instrument's direct measurements. Each spacecraft was powered by 3 radioisotope thermoelectric generators, metal cylinders containing pellets of plutonium-238, whose natural radioactive decay produced heat that was converted directly into electricity by thermoelectric junctions, requiring no moving parts. At launch, those generators collectively produced about 470 watts per spacecraft, barely enough to power a few incandescent light bulbs by today's standards, but sufficient to run a carefully prioritized selection of instruments. The power would decline by a few watts every year as the plutonium decayed. The engineers designed the mission to manage that decline, building in the ability to turn instruments off one by one over the decades to conserve electricity for the instruments most critical to the outer solar system science. Every decision about what to keep and what to sacrifice had been made before launch and written into the mission plan. Those decisions, made in the early 1970s by people who could not have imagined how long the mission would actually run, shaped what data would come back from the very edge of the solar system. Voyager 2 launched first, on August 20th, 1977. Voyager 1 followed 16 days later, on September 5th. Despite leaving second, Voyager 1 was sent on a faster, steeper trajectory and quickly overtook its twin, which is how the later launched spacecraft came to be the one that traveled farther and faster. Both carried copies of the Golden Record, a 12-inch disc of gold-plated copper encoded with 115 images of Earth and its life, greetings spoken aloud in 55 different human languages, and an audio track containing natural sounds ranging from breaking ocean waves to a chimpanzee greeting to a humpback whale song, along with music from 27 different cultural traditions spanning every inhabited continent. The music selections included compositions by Bach and Beethoven, a piece by Chuck Berry, a Navajo night chant, a Peruvian wedding song, a piece of traditional Bulgarian choral music, and field recordings of music from Indonesia, Japan, Australia, Senegal, and more. The cover of each record was engraved with diagrams explaining how to decode it using a rotating needle, geometric principles about binary encoding, and a diagram of the hydrogen atom providing a universal unit of measurement. The designers understood that these machines would almost certainly outlast every human civilization, every language spoken today, and possibly the star-warmed planet that produced them. The records were a statement about what human civilization chose to do when it became aware that it was sending objects into the galaxy. They were messages to the incomprehensible future. The primary mission was something more immediate, but the record's mission had no end date. It continues now and will continue for billions of years. Before any of that distant future could unfold, the spacecraft had planets to visit, and the planets had surprises ready. Jupiter was first. and Jupiter set the tone for everything that followed. When Voyager 1 arrived at Jupiter in March 1979, it was moving quickly. The entire encounter from close approach to departure spanned only a few days, and every instrument was running continuously. The science teams had hoped for dramatically sharper images of Jupiter's cloud bands and storms than any Earth-based telescope could provide, and they got those. The famous Great Red Spot, a storm larger than Earth that had been observed from Earth for centuries, was revealed in extraordinary detail as a complex, structured cyclone with layers of cloud rotating at different speeds. The bands of Jupiter's atmosphere showed turbulence and wave structures and subtle color variations that would provide atmospheric scientists with enough material to analyze for years. But then something happened that none of the planning documents had anticipated. A few days before the spacecraft's closest approach to Jupiter, a navigation engineer was processing long-exposure images of the star field near the moon Io, using background stars to pin down the spacecraft's precise position. In one of those images, extending above Io's curved horizon against the black sky behind it, was a bright, irregular smear. The engineer studied it carefully. The smear had internal structure. It was not an artifact. It was a plume rising from Io's surface, arching hundreds of miles into space in the shape of an umbrella. She had found the first active volcanic eruption ever confirmed outside of Earth. Io, a moon slightly smaller than Earth's own moon, was supposed to be a cold, dead rock. The outer solar system's moons were expected to be geologically inert, frozen in the conditions of the early solar system. Instead, Io's surface was being continuously reshaped by volcanic eruptions driven by a heat source that nobody had thought would be significant: tidal flexing. Jupiter's enormous gravity constantly stretched and squeezed Io's interior as the moon followed its slightly elliptical orbit, generating frictional heat deep in the rock at rates far exceeding the internal heat of the Earth. That heat had to go somewhere. It escaped through volcanoes that coated Io's surface in fresh sulfur compounds in yellows and oranges and reds, erasing impact craters as fast as new impacts could create them, making Io one of the youngest surfaced bodies in the solar system, despite being billions of years old. The concept of tidal heating, which this discovery forced scientists to take seriously, would eventually become one of the most important ideas in astrobiology, because it meant that moons of giant planets could harbor liquid interiors warmed by gravity even in the cold outer solar system. Even in the dark regions far from their stars' warmth, the Io discovery established what would become the pattern of the entire Voyager mission. Wherever the spacecraft looked, what they found exceeded what the models had predicted. The outer solar system was not the quiet, frozen, well-understood region that the prevailing view had depicted. It was full of active processes, unexpected chemistry, surprising geology, and physical conditions that the best available theories had underestimated or missed entirely. The science teams quickly learned to hold their predictions lightly and to read the incoming data with fresh eyes. That habit of expectation-free observation would serve them extremely well when the spacecraft finally reached the outer boundary of the solar system and found conditions that were wrong in almost every specific detail the models had forecast. Saturn was next. Voyager 1 arrived in November 1980, and what its cameras revealed in the ring system stunned even the scientists who had spent years preparing for it. From Earth, Saturn's rings appear as a small number of broad, smooth, symmetric bands, elegant and simple. Under Voyager's cameras, those broad bands dissolved into a structure of overwhelming complexity. Thousands of individual ringlets, each one a narrow lane of orbiting ice particles and rocky chunks, separated by gaps that were sometimes sharp and crisp, and sometimes fuzzy and gradually transitioning. Some ringlets were braided, 2 or 3 strands wound around each other, in a repeating pattern that simple orbital mechanics said should not persist. Those braided structures were gravitationally sustained by small shepherd moons embedded in the ring system, tiny bodies whose orbits ran just inside and outside the braided rings, and whose gravitational influence herded the ring particles into the anomalous configuration. Other rings had such sharp outer edges that they seemed cut by a precise instrument maintained against the natural tendency of orbiting material to spread by the gravitational sweeping action of shepherd moons on their outer boundaries. Spiral density waves rippled through the ring material from locations determined by gravitational resonances with Saturn's larger outer moons, wave patterns that carried information about the ring's physical properties, its mass per unit area, the velocity dispersion of the particles, the balance between self-gravity and collisional pressure, in a way that ring scientists could read like text once they had the theoretical tools to decode it. The scale of the structure was also startling. The rings spanned a distance from Saturn's cloud tops of roughly 40,000 miles on the inner edge to almost 90,000 miles on the outer edge of the main ring system, yet they were in places only a few dozen feet thick, a physical ratio comparable to a sheet of paper the size of a football field. Something about the dynamics of orbiting particles, interacting gravitationally with each other and with the nearby moons, had organized all that material into an extraordinarily thin disk with an extraordinarily complex internal structure. The rings were a laboratory for orbital dynamics operating at scales and timescales that no Earth-based experiment could replicate. Then the team made the decision that permanently shaped Voyager 1's role in the mission. Titan, Saturn's largest moon, was wrapped in an orange atmospheric haze that blocked optical cameras from seeing its surface. But everything the instruments could measure about that atmosphere made it scientifically overwhelming. The atmosphere was dense, denser than Earth's at the surface, and composed mostly of nitrogen with significant methane. Chemical reactions driven by solar ultraviolet radiation were converting the methane into a complex mixture of more complicated organic molecules that rained down onto the surface as an orange smog. Models suggested the surface might harbor pools or even seas of liquid methane and ethane, too cold for water to be liquid, but the right temperature for those heavier hydrocarbons to exist in liquid form. Getting a close pass at Titan required using Titan's gravity to redirect Voyager 1's path, and the required deflection was steep. The spacecraft was bent roughly 35 degrees above the plane in which all the planets orbit, the ecliptic plane. That meant Voyager 1 would be aimed above and away from the solar system's flat disk, on a trajectory that would carry it into the outer solar system at a steep angle, heading roughly in the direction of the boundary of the heliosphere in the northern hemisphere. There would be no more planets, no Uranus, no Neptune, no further flybys, just the long outward climb into the dark. The team knew exactly what they were trading and made the decision deliberately. In doing so, they aimed Voyager 1 directly toward what would eventually become the first crossing of the solar system's outer boundary by any human-made object. While Voyager 1 climbed above the plane and outward, Voyager 2 continued on its broader tour. It reached Uranus in January 1986, finding a planet stranger than anything in the textbooks. Uranus rotates essentially on its side, its axis tilted nearly 90 degrees from vertical relative to its orbit. The most widely accepted explanation is a giant impact early in the solar system's history. Some large object struck Uranus with enough force to topple it, and it has been rolling sideways ever since. The consequences for Uranus's seasons are dramatic. Each of the planet's poles faces the star for about 42 years at a stretch before the orbit carries it into decades of darkness. Voyager 2 reached Uranus near the southern pole's period of full illumination, meaning the cameras were looking almost directly down on one pole for most of the encounter. The planet's atmosphere was far less visually dynamic than Jupiter's or Saturn's, a featureless pale blue-green disk in visible light, though infrared imaging revealed temperature structures and the ultraviolet spectrometer detected atmospheric chemistry. The moons of Uranus were the real surprise. Voyager 2 found 5 major moons, all showing evidence of geological activity far more complex than cratered and dead ancient surfaces. Miranda, the smallest and innermost of the large moons, was a geological puzzle, terrain ranging from ancient, heavily cratered plains to regions of young, grooved terrain with enormous fault systems and cliffs up to 5 miles high, all seemingly jumbled together without obvious organizational logic. The original explanation, a shattering collision followed by gravitational reassembly, has largely given way to models invoking internal heating and resurfacing. But Miranda remains one of the least understood major moons in the solar system. Neptune was the final planet. Voyager 2 arrived in August 1989, 12 years after leaving Earth, operating on systems designed to last 5. Neptune was cold and deep blue and extraordinarily dynamic. Wind speeds in its upper atmosphere exceeded 1,000 miles per hour, the fastest winds measured anywhere in the solar system at that time, despite Neptune being so far from the star that the available solar energy driving atmospheric circulation is just a tiny fraction of what drives Earth's weather. Some of Neptune's atmospheric energy must come from internal heat, residual warmth from the planet's formation still leaking out through the gas. A dark storm the size of Earth churned in the southern hemisphere. Voyager 2 found 6 new moons around Neptune and confirmed the existence of rings, narrow and dark, and made of material with very low reflectivity. The largest moon, Triton, was the most remarkable. Triton orbits Neptune in the wrong direction, a retrograde orbit, circling opposite to Neptune's own rotation. This orbital signature is the hallmark of a captured body, and Triton is believed to have been a free-orbiting body in the outer solar system that drifted too close to Neptune billions of years ago and was gravitationally captured. Its surface was extraordinarily cold, among the coldest solid surfaces measured in the solar system, yet it was not geologically quiet. Jets of dark material erupted from below the surface ice, driven by the tiny amount of solar energy that penetrated the transparent nitrogen ice on the surface and vaporized nitrogen gas below, which then forced its way through the ice in narrow geysers that rose miles into the thin atmosphere before the plumes bent sharply downwind. These cold nitrogen geysers on a captured moon at the edge of the planetary system were the last major discovery the Voyagers made during their planetary tour, and then Neptune was behind them. The planetary system was finished. Both spacecraft were heading into territory that had never been explored. Beyond the planets lay the outer heliosphere, and what science knew about this region came entirely from theory, not measurement. The picture was logically constructed but entirely untested. Every second, the star at the center of the solar system ejects a continuous stream of charged particles, electrons and protons, in all directions at speeds of roughly 1,000,000 miles per hour. This outflow is called the solar wind, and it creates a vast, dynamic, magnetized bubble around the solar system called the heliosphere. That bubble extends outward in all directions until the solar wind's pressure is balanced by the pressure of the gas and magnetic fields that fill the space between stars. Where the solar wind first collides with interstellar pressure and abruptly slows, the boundary is called the termination shock. Beyond that, in the heliosheath, the slowed and compressed solar wind continues outward before reaching the heliopause, where the balance between inward interstellar pressure and outward solar wind pressure is exact, and the solar wind stops flowing. Beyond the heliopause is interstellar space, a different physical environment governed by processes originating at other stars and throughout the galaxy, not at the star we orbit. Models predicted the termination shock somewhere between 70 and 90 astronomical units from home. 1 astronomical unit is the distance from Earth to the star, roughly 93 million miles. 90 astronomical units is about 8 billion miles from Earth. The heliosheath beyond the shock would be perhaps 10 to 20 astronomical units thick. The heliopause would be the sharp transition into the interstellar medium. All of these predictions were built from solid physics and carefully constructed models. All of them were about to be tested by the most rigorous test that exists in science: actual measurement. The Voyagers were the first instruments ever positioned to make those measurements. What they found would force the entire field of heliospheric physics to revise its models repeatedly and thoroughly over the following 2 decades. The theory underlying those predictions had been built up patiently over decades. The solar wind itself was first predicted in the late 1950s, when a physicist realized that the star's outer atmosphere, the corona, was so hot that the outer layers could not be held in place by the star's gravity and had to be streaming continuously outward into space. Early spacecraft in the 1960s confirmed the solar wind existed. Later missions measured its average properties near Earth, a density of roughly 5 to 10 protons per cubic centimeter, a velocity of about 300 to 500 miles per second, and a temperature of roughly 100,000 degrees. Embedded in this outflow was a magnetic field, the star's own field carried outward by the flowing plasma. As the solar wind expanded outward through the solar system, it thinned and cooled. By the time it reached the outer planets, its density had dropped by billions of times compared to near the star. What happened to the solar wind when it finally ran into the interstellar medium was the key question. The interstellar medium in the solar system's neighborhood is not a vacuum. It is a dilute plasma of its own, electrons and ions left over from ancient stellar explosions and the general interstellar environment, with a density of perhaps 1 particle per 10 cubic centimeters, thousands of times less dense than the solar wind near Earth, but present everywhere in the space between stars. It carries magnetic fields too, organized on large scales by galactic dynamics, and on small scales by the turbulence of old supernova remnants. As the solar wind expands outward and loses pressure, there comes a distance where the solar wind's outward push can no longer overcome the interstellar medium's inward pressure. At that distance, the fast-moving solar wind must slow down abruptly, just as fast water in a stream slows and piles up when it hits a slow-moving pool. The abrupt slowdown is the termination shock, and it was expected to heat the solar wind plasma significantly, converting the directed kinetic energy of the streaming solar wind into the random thermal motion of the plasma particles. The heliosheath, the thick region between the termination shock and the heliopause, was expected to be filled with this hot, slowed solar wind piling up against the outer boundary. Beyond the heliopause, the interstellar medium stretched outward in all directions, the same environment that fills the space between stars across the entire galaxy. The models also made specific predictions about a class of energetic particles called anomalous cosmic rays. These particles were first detected by earlier spacecraft in the 1970s. They had energies much higher than the average solar wind particle, but lower than the galactic cosmic rays that constantly bombard the solar system from outside. They had an unusual composition, being enriched in elements like oxygen and helium that are common in the interstellar medium. The theoretical explanation that gained the most support was a multi-step process. Neutral atoms from the interstellar medium drifted into the heliosphere and were ionized, either by charge exchange with solar wind protons or by the star's ultraviolet radiation. The newly ionized particles were then picked up by the solar wind's magnetic field and swept outward. As they reached the termination shock, the conditions there were expected to efficiently accelerate some fraction of these picked-up ions to the high energies observed. The termination shock, in this picture, was a particle accelerator built by the collision of the solar wind with interstellar space. The anomalous cosmic rays would peak in intensity right at the shock or just inside it, their acceleration source. This prediction was clean, well supported by the physics, and completely wrong. What the models also predicted, with considerable confidence, was that the heliosphere would be roughly symmetric, not a perfect sphere, since the solar system's motion through the galaxy would press the interstellar medium harder against the nose of the heliosphere, but a shape whose scale was similar in most directions. The termination shock at 90 AU in one direction should be found at roughly similar distances in other directions, perhaps varying by 10 or 20% depending on the local interstellar wind pressure. The heliopause should be similarly smooth and predictable. These symmetry assumptions made the models tractable. They reduced a complicated three-dimensional problem to something closer to one-dimensional in the radial direction. They would later turn out to be wrong in ways that revealed deep truths about both the interstellar environment surrounding the solar system and the dynamics of how the solar wind interacts with it. The spacecraft themselves were aging as they approached the outer heliosphere. The camera platforms that had captured the first close views of other planets had been powered off to save energy. The power budgets were tightening year by year. Yet, the fundamental measurement instruments, the charged particle detectors, the magnetometers, the plasma wave systems, and on Voyager 2 the plasma science instrument, were still working. They were aging gracefully, their measurements continuing to meet calibration standards even after years of radiation exposure, temperature cycling, and operation in conditions far more extreme than they had been qualified to survive. The mission that had been designed to last 5 years was entering its second decade with science quality instruments still returning data. The outer heliosphere was ahead. The termination shock was ahead. Everything the models predicted was waiting to be tested by the only instruments in position to test it. And the data that came back would change the picture of the outer solar system more completely than anyone had anticipated. The approach to the termination shock was not a sudden event. It was years of data showing gradual changes in the particle populations and the magnetic field. As Voyager 1 pressed outward through the 1990s and into the 2000s, the charged particle instruments tracked the slow decline in solar wind particle density and the slow increase in anomalous cosmic ray intensity. Each passing year added a little more distance between the spacecraft and the star, and each passing year the instruments registered the gradual shift from a solar-dominated environment towards something different. The outer solar system was not empty space. It was full of particles carrying the history of the solar wind's outward passage. Particles that had been accelerated and scattered and heated and cooled over the billions of miles between their origin at the star and their detection by the instruments. The outer solar system is also where the solar wind encounters the first signs of the interstellar medium drifting inward. Neutral hydrogen atoms from interstellar space can cross the heliopause and drift inward through the heliosphere. Since they carry no charge and are not deflected by the heliospheric magnetic field, they move slowly relative to the solar wind at a few dozen miles per second rather than a few hundred, and they fill the entire heliosphere. When those neutral hydrogen atoms encounter the solar wind's protons, a fraction of them undergo charge exchange. The proton takes the electron from the hydrogen atom, creating a new neutral hydrogen atom that flies off in a straight line, carrying the proton's energy and leaving behind a new, slower proton that gets picked up by the solar wind's magnetic field. These pickup ions, interstellar atoms that have been ionized and added to the solar wind, build up in density as the solar wind moves outward and encounters more and more interstellar neutral material. Near the termination shock, pickup ions could represent a significant fraction of the total particle population. Their presence was predicted, and instruments on the Voyagers were sensitive enough to detect their effects, even if not optimally designed to characterize them in detail. Then, in 2002 and 2003, the charged particle instruments on Voyager 1 began showing unusual behavior. The intensity of anomalous cosmic rays and other energetic particles started fluctuating in a way that suggested the spacecraft was experiencing changes in its magnetic environment, possibly the influence of the termination shock moving toward and then away from the spacecraft's position. The termination shock is not a fixed boundary. The solar wind's pressure varies over the 11-year solar activity cycle, and as solar activity rises and falls, the solar wind's outward pressure changes, which pushes the termination shock outward during periods of high solar activity and allows it to contract inward when the solar wind weakens. In 2002, the star was emerging from a period of high activity, and the solar wind pressure was declining. The termination shock appeared to be moving inward, possibly passing over Voyager 1 temporarily. The spacecraft may have briefly crossed into the heliosheath and then been pushed back out as the shock moved outward again. The data from this period was ambiguous and generated significant debate among the science team. Some argued the spacecraft had made a partial crossing. Others maintained it was still well inside the termination shock. The debate highlighted something important. The boundary was not sitting still, and it was not necessarily a sharp, simple transition that would be instantly obvious when the spacecraft crossed it. The termination shock was a dynamic structure, breathing in and out with the solar wind's varying pressure, and approaching it was not going to be straightforward. By late 2004, Voyager 1 was at approximately 94 astronomical units, over 8.5 billion miles from the center of the solar system. The charged particle instruments were showing sustained changes. The magnetic field was fluctuating. In December 2004, multiple instruments simultaneously showed the signatures that the science team had defined in advance as proof of a termination shock crossing. The anomalous cosmic ray intensity made a sustained jump. The magnetic field showed the expected compression, and the low-energy charged particle instrument recorded the dramatic slowdown in solar wind particle velocities. The solar wind, which had been flowing outward at roughly 300 miles per second at the spacecraft's position, slowed to under 100 miles per second over a zone only a few astronomical units thick. Voyager 1 had crossed the termination shock. The milestone the mission had been building toward for 27 years had finally arrived. The measurements coming back were immediately interesting and immediately wrong. The first major finding was the magnetic field orientation. Before the crossing, the models had predicted that the solar wind's magnetic field would be compressed and reorganized at the termination shock in a specific way, with the field direction rotating to reflect the change in solar wind conditions. The actual field direction on the far side of the shock was rotated by nearly 30 degrees from the predicted orientation. 30 degrees seems minor until you understand that this was a systematic, reproducible measurement from a well-calibrated instrument. Not noise, not an artifact, but a real discrepancy between what the models said should be there and what was actually there. The heliosphere's magnetic structure near the termination shock was organized differently from the model's predictions. The magnetic geometry of the outer heliosphere was wrong in the pre-Voyager models. That finding alone was enough to generate a wave of theoretical work aimed at understanding what the actual structure was and why the predictions had been off. And it was only the beginning. The termination shock crossing confirmed something the theoretical community had begun to suspect, but had not been able to test. The heliosphere is not symmetric. The solar system is not sitting at the center of a perfectly uniform bubble of solar wind pressure. Instead, the interstellar environment surrounding the heliosphere has structure, regions of higher and lower pressure, a magnetic field that is organized and directional, an interstellar wind that flows past the solar system at tens of miles per second. The termination shock is shaped by all of these external forces pressing against it. Where the interstellar wind is strongest, the shock is pushed closer to the star. Where the interstellar magnetic field is oriented to reinforce the pressure, the shock is compressed further. The 30-degree discrepancy in the magnetic field orientation at the shock was a direct measurement of how wrong the symmetry assumption was. The solar system's magnetic environment is not an island unto itself, passively sitting in an inert interstellar medium. It is in active, dynamic equilibrium with a structured galactic environment that exerts real forces on it in specific directions, and those forces are not symmetric. That asymmetry, confirmed by the termination shock crossing, would be reinforced and extended by every subsequent measurement in the outer heliosphere. The heliosphere was a more complex and more tightly coupled structure than anyone had modeled, embedded in an interstellar environment that was more organized and more influential than the pre-Voyager picture had assumed. What awaited the spacecraft beyond the termination shock would deepen this picture considerably. 3 years after Voyager 1's crossing, in August 2007, Voyager 2 arrived at the termination shock. It crossed at approximately 84 astronomical units, nearly 10 astronomical units closer to the center of the solar system than Voyager 1's crossing point. 10 astronomical units is roughly 930 million miles. That difference between the two crossing distances was immediately significant. If the heliosphere were a symmetric bubble, the same distance to the shock in all directions, both spacecraft should have crossed at roughly the same distance, regardless of the direction they were traveling. The 10-unit discrepancy meant the heliosphere was distinctly asymmetric. Its southern hemisphere, where Voyager 2 was headed, had a smaller radius than its northern hemisphere. Something was squeezing the heliosphere's southern boundary closer to the star than the northern boundary. The explanation pointed outward, not inward. The solar system is moving through the galaxy at roughly 52,000 miles per hour relative to the local interstellar medium. As it moves, the interstellar gas and magnetic field are not uniform in all directions. The interstellar wind, the flow of interstellar material relative to the solar system, presses harder against the side of the heliosphere it is flowing toward, compressing the boundary there. The local interstellar magnetic field is also organized along a specific direction, and it exerts a pressure on the heliosphere that varies depending on the angle between the field lines and the heliosphere's boundary in each region. The combination of the interstellar wind and the interstellar magnetic field creates a pressure environment that is stronger in some directions than others, and the southern hemisphere of the heliosphere appears to face higher interstellar pressure than the northern hemisphere does. That pressure difference compresses the southern boundary closer to the star, which is why Voyager 2 found the termination shock 10 astronomical units closer in than Voyager 1 did. The heliosphere's shape is determined by both the solar wind pushing outward and the interstellar environment pushing back, and that environment is structured in ways that create a distinctly asymmetric bubble. Voyager 2's crossing provided something that Voyager 1's crossing in 2004 had been unable to offer: direct plasma measurements. Voyager 1's plasma science instrument had failed in 1980, more than 20 years before its termination shock crossing. Without that instrument, the science team at Voyager 1's crossing had to infer plasma conditions from changes in the magnetic field and the charged particle instruments. Rather than measuring the solar wind's temperature, density, and velocity directly, Voyager 2's plasma instrument was still working, and that made its termination shock crossing one of the most scientifically valuable events in the entire Voyager mission. For the first time, a spacecraft with a functioning plasma instrument was crossing the solar system's first outer boundary. The data it returned immediately created a significant problem for the models. The termination shock is the place where the fast-moving solar wind first collides with the slower medium on the other side and abruptly decelerates. In plasma physics, this kind of abrupt deceleration is called a shock, and shocks are efficient converters of kinetic energy, the energy of directed motion, into thermal energy, the energy of random particle motions we measure as temperature. The incoming solar wind was moving at roughly 300 miles per second. On the far side of the shock, it was moving at under 100 miles per second. All that kinetic energy of the deceleration had to go somewhere. The models, using well-established plasma shock physics, predicted that most of it would go into heating the plasma. The electrons and protons in the solar wind should be heated dramatically at the shock. The models predicted plasma temperatures of roughly 1.5 million degrees just beyond the crossing. Voyager 2 measured approximately 180,000 degrees. That is about 12% of the predicted value. The other 88% of the expected thermal energy was not in the plasma that the instruments could measure. It had gone somewhere else. Or the physics of energy conversion at this particular type of shock was different from what the models assumed. Where did the energy go? That question became one of the most actively discussed problems in outer heliosphere physics in the years after Voyager 2's crossing. Several possibilities were proposed. One was that the energy went into heating heavier ions, atoms heavier than protons, like oxygen, helium, and heavier elements that are present in the solar wind at lower concentrations, that the plasma science instrument was not well suited to characterize. Some energy certainly went into accelerating the anomalous cosmic rays, which are known to be energized somewhere in the outer heliosphere. Some may have been converted into wave turbulence in the magnetic field, which dissipates differently from direct plasma heating. But adding up reasonable estimates of all these alternative sinks, researchers could not fully account for the missing 88%. The numbers didn't balance. Either the measurements had systematic errors that couldn't be identified, or there was a physical process operating at the termination shock that was not in any of the models. The missing energy at the termination shock remains one of the unresolved puzzles of outer heliosphere physics. It is a vivid example of the kind of specific, quantitative wrong that the Voyager data produced in what had been considered well-understood theoretical territory. Beyond the termination shock lay the heliosheath, the buffer zone between the shock and the true edge of the solar system at the heliopause. The models had depicted this region as a moderately turbulent zone, where the slowed solar wind would gradually transition toward the conditions that prevailed just inside the heliopause. Both spacecraft would spend years in the heliosheath, and during those years, the data they sent back described a region that was far more complex, far more spatially variable, and far more energetically active than the models had suggested. The magnetic field in the heliosheath showed large amplitude fluctuations on timescales of hours to days, fluctuations far exceeding the gentle variations the models had predicted. Energetic particles were distributed in sharp, discrete layers, rather than the broad, diffuse distributions the models assumed. The plasma temperature showed unexpected variations in both directions, some regions cooler than expected, others warmer, with no clear pattern tied to distance from the termination shock. The heliosheath was not a simple, gradual transition zone. It was a complex, structured environment with its own internal dynamics. Among the most important heliosheath findings was the behavior of the anomalous cosmic rays. These moderately energetic particles, which had been a focus of outer heliosphere physics for decades, were predicted to peak in intensity right at or just inside the termination shock, the place where they were supposedly being created by the shock acceleration process. Instead, both spacecraft found that anomalous cosmic ray intensity continued increasing well beyond the termination shock, deeper into the heliosheath. They were more intense far from the shock than at the shock itself. This was a direct contradiction of the acceleration model. If the termination shock were the primary source, intensity should peak there and fade with increasing distance from the source. The fact that it kept rising deep into the heliosheath meant either that the particles were being accelerated somewhere else and diffusing back into the heliosheath from another direction, or that the transport of these particles through the complex heliosheath magnetic field was so different from the model's assumptions that particles from a distant source appeared to be concentrated closer to the heliopause. The most widely discussed alternative explanation pointed to the flanks and tail of the termination shock rather than the nose region that the Voyagers had sampled. The termination shock is not a simple flat wall. It is a three-dimensional surface surrounding the entire solar system, and its properties vary considerably around its perimeter. The nose of the termination shock, facing the direction the solar system moves through the interstellar medium, is where the solar wind most directly impacts the interstellar pressure. The flanks, on the sides, and the tail, behind the solar system in the direction it is moving away from, have different geometries and different flow conditions. Some theoretical work suggested the flanks might be more efficient particle accelerators than the nose, perhaps because the geometry of the magnetic field at the flanks is more favorable for the repeated reflection and acceleration that generates high-energy particles. If most anomalous cosmic ray acceleration happens at the flanks of the termination shock, the particles would diffuse inward from the flanks and be found throughout the heliosheath rather than concentrated near the nose where the Voyagers crossed. This explanation is plausible and consistent with the data, but it cannot be confirmed without measurements from the flanks, regions the Voyagers never visited and no other spacecraft is positioned to study. Deep in the heliosheath, Voyager 1 encountered something that stopped the scientific team in its tracks. In 2010, the low-energy charged particle instrument registered that the outward flow of solar wind particles had dropped to essentially zero. The solar wind was no longer streaming outward from the star in the direction Voyager 1 was traveling. At a position then, about 113 astronomical units from the center of the solar system, still well inside the heliosphere, the solar wind had simply stopped flowing outward. This was not predicted. Every model of the heliosheath assumed the solar wind would continue flowing outward, slowly and compressed, until it reached the heliopause and stopped there. The discovery that the flow halted well before the heliopause implied that the solar wind was being deflected sideways, redirected around the edges of the heliosphere, rather than flowing straight outward through it to the heliopause. Something in the outer heliosheath was turning the solar wind aside before it could reach the boundary. The most likely culprit was the pressure and magnetic tension of the interstellar medium just outside the heliopause, which was strong enough in this direction to prevent the solar wind from penetrating all the way to the boundary. The solar wind was being turned aside, flowing around the outer edges of the heliosphere in the heliosheath rather than pushing straight through to the heliopause. The region where this happened came to be called the stagnation region, a term that captured the absence of the expected outward flow. Within the stagnation region, Voyager 1 found something remarkable and unexpected in the magnetic field data. Field lines, threading through the stagnation region, appeared to be connecting the inside of the heliosphere to the outside, running through the heliopause, rather than being deflected by it. Energetic particles were streaming along these field lines in both directions simultaneously, galactic cosmic rays flooding inward from interstellar space, and solar energetic particles leaking outward toward it. The heliosphere's outer wall was not sealed. It was threaded by magnetic pathways that allowed material to pass in both directions. Some members of the science team described these pathways as a magnetic highway, a network of connected field lines along which particles could travel between the interior of the heliosphere and interstellar space. The concept challenged the picture of the heliopause as an impermeable barrier and raised questions about how cleanly separated the heliospheric and interstellar environments actually are at the boundary. Magnetic reconnection, the process by which magnetic field lines from two different regions break and reconnect with field lines from the other region, was the most natural explanation for how field lines from opposite sides of the heliopause could end up connected. Reconnection is a process known from many other contexts in plasma physics, including at Earth's own magnetosphere, where the solar wind's magnetic field regularly connects with Earth's field to allow particle exchange across the magnetopause. Finding evidence for it at the outer edge of the heliosphere added the solar system's boundary to the list of environments where this fundamental plasma process operates. By 2012, the particle environment around Voyager 1 changed more dramatically than anything since the termination shock crossing. Over a period of roughly 3 days in mid-August 2012, the low-energy charged particle instrument recorded a sharp, sustained drop in the flux of particles associated with the solar wind. Simultaneously, the cosmic ray instrument registered a jump in the intensity of galactic cosmic rays, high-energy particles from sources throughout the galaxy, accelerated by supernova remnants and other energetic processes far outside the solar system. The galactic cosmic ray flux climbed to the highest level Voyager 1 had ever recorded and then plateaued, suggesting the spacecraft had crossed into a region fully saturated with the unshielded galactic radiation environment. The change was dramatic and rapid. The transition from inside to outside appeared to have happened within a very short distance. But the magnetic field told a more complicated story. One faction of the science team held that crossing the heliopause should bring a large rotation in the magnetic field direction, possibly as much as 90 degrees, as the field transitioned from the heliospheric structure dominated by the solar wind to the interstellar structure dominated by the galactic magnetic field. The field rotation that accompanied the particle changes in August 2012 was substantial but much less than 90 degrees. Some scientists argued this meant Voyager 1 was in a new, unmapped region, neither fully inside the heliosphere nor fully in true interstellar space. They proposed that the spacecraft might be in a region where the heliospheric and interstellar magnetic fields had already mixed, perhaps through the reconnection processes hinted at in the stagnation region. Others argued that the particle changes were definitive and that Voyager 1 had crossed the heliopause regardless of what the magnetic field did, because the particle population had entirely changed character. The debate was substantive and public, playing out in scientific papers and at conferences for over a year. The decisive measurement came from the plasma wave instrument. The plasma wave system detects oscillations in the surrounding ionized gas, specifically the vibrations that electrons in a plasma undergo at a frequency determined by the electron density. These oscillations can be excited by shocks and pressure waves traveling through the plasma. In April 2013, 9 months after the dramatic particle changes of August 2012, a pressure wave generated by a solar eruption reached Voyager 1's position after propagating outward from the star for over a year. As the pressure wave compressed the local plasma, it drove electron plasma oscillations that the plasma wave instrument detected. The frequency of those oscillations provided the electron density directly. The measured density was approximately 0.08 electrons per cubic centimeter. That density was about 40 times higher than anything measured inside the heliosphere. It precisely matched theoretical predictions for the local interstellar medium. Voyager 1 was well outside the heliopause, sampling interstellar plasma directly. The spacecraft had entered interstellar space in August 2012. The confirmation came in April 2013. NASA announced the milestone officially in September 2013. The announcement was historic. Voyager 1 had become the first human-made object in history to leave the solar system and enter interstellar space. The signal carrying that news from Voyager 1 to Earth had traveled for approximately 17 hours to arrive. The spacecraft was at that point roughly 122 astronomical units from the center of the solar system, about 11.5 billion miles from home. The achievement was the result of decades of careful engineering, thoughtful science planning, and more than a little extraordinary luck, but it was immediately followed by new findings that complicated the picture. The plasma density measurement was not what the models had predicted. The density in the local interstellar medium, just outside the heliopause, was higher than most pre-Voyager models had estimated. Higher density means higher pressure, which means the interstellar medium is pushing harder against the heliosphere's outer wall than the models assumed. That has direct consequences for the heliosphere's size. A stronger external pressure requires a stronger solar wind pressure to maintain equilibrium at the heliopause, meaning the equilibrium point is closer to the star than it would be in a lower density interstellar medium. The higher than expected density was part of why the termination shock and heliopause were found at somewhat different distances than the model predictions, though the exact relationship between density, pressure, and boundary location involves multiple competing factors. What it meant clearly was that the interstellar neighborhood the solar system occupies is denser and more pressurized than the pre-Voyager models had assumed. The magnetic field finding at the heliopause also required explanation. Models predicted a large rotation in field direction at the crossing because the heliospheric field and the interstellar field were expected to be oriented very differently. The modest rotation that was actually observed meant the two fields were nearly parallel near the heliopause. The interstellar magnetic field in the solar system's immediate neighborhood was oriented similarly to the heliospheric field rather than perpendicular to it. This had implications for how the heliosphere's nose was shaped. When an external magnetic field is nearly parallel to the surface of the heliosphere at the nose, its interaction with the heliospheric field is different from the case where the two fields are perpendicular. The shape of the heliosphere's nose, whether it is blunt or tapered, Whether it has a bow shock in front of it or just a bow wave depends sensitively on this geometry. The nearly parallel field orientation discovered by Voyager 1 suggested the heliosphere's interaction with the interstellar medium near its nose was different in character from what the models had described. Voyager 2's The Crossing of the Heliopause in November 2018 provided a second look at this boundary from a different direction. It crossed at approximately 119 astronomical units from the center of the solar system, about 3 astronomical units closer than Voyager 1's crossing. The difference in crossing distance confirmed the asymmetry already suggested by the different termination shock crossing distances. The heliosphere does not have the same radius in all directions. The direction that Voyager 2 traveled, below the ecliptic plane, toward the southern galactic hemisphere, apparently faces slightly higher interstellar pressure than the direction Voyager 1 traveled, compressing the heliopause closer to the star. Voyager 2's crossing had the enormous advantage of a functioning plasma science instrument. For the first time, scientists could directly measure the plasma properties right at the heliopause, on both sides of the boundary. The data arriving from Voyager 2 over the days of its crossing showed the transition from inside to outside with a precision and directness that Voyager 1's indirect methods could not provide. On the inside of the heliopause, in the outermost heliosheath, the solar wind plasma was hotter than expected, hotter than it had been at the termination shock. This was backward from the simple cooling with distance model. The plasma should have been cooling as it decelerated through the heliosheath and moved away from the energetic termination shock region. Instead, it was being heated somewhere in the outer heliosheath. The energy source for that heating was not immediately identifiable. Charge exchange between solar wind protons and interstellar neutral hydrogen atoms was one candidate. This process can transfer energy from the neutral hydrogen into the plasma. Wave heating, in which the constant fluctuations of the magnetic field in the turbulent heliosheath gradually convert magnetic energy into plasma heat, was another. No single mechanism cleanly explained the measured temperatures, and the combination of mechanisms required to account for the observations was itself informative about the complex energy budget of the outer heliosheath. At the heliopause itself, the plasma transition was sharp. Both spacecraft found that the change from heliospheric to interstellar plasma conditions happened within a very narrow zone, just a few astronomical units thick, sometimes less. The heliosphere did not fade gradually into the interstellar medium. It ended abruptly, the way a soap bubble ends at its surface, rather than gradually thinning out into surrounding air over a long distance. The sharpness of the heliopause surprised many researchers who had expected a thicker, more diffuse transition zone. The sharp boundary implied that the heliopause was a stable, well-defined surface in magnetic and plasma pressure equilibrium, not a turbulent mixing zone where the two environments blended over large distances. On one side of this thin surface, the heliosphere, with its solar wind plasma and solar-dominated magnetic field. On the other side, the interstellar medium, with its denser plasma, higher magnetic field strength, and galactic, cosmic ray environment. Two fundamentally different physical environments, separated by a boundary you could cross in a few months of spacecraft travel time. Just outside the heliopause, the interstellar plasma properties that both spacecraft measured told a story about the environment the solar system is currently moving through. The magnetic field strength just outside Voyager 2's crossing point was slightly higher than what Voyager 1 had measured at its crossing point on the other side of the heliosphere. This confirmed that the interstellar magnetic field is not uniform around the solar system's position. It has structure on scales comparable to the heliosphere itself, varying from one side of the heliosphere to the other. The interstellar plasma temperature in the immediate vicinity of both crossings was in the range of 30,000 to 50,000 degrees, hotter than cold neutral interstellar medium, but consistent with what is called the warm ionized interstellar medium, a phase of the interstellar environment known from observations of distant stars. The solar system is not sitting in a quiet, cold cloud of neutral gas. It is embedded in a warm, partially ionized interstellar environment that has its own dynamics and structure. One of the most important quantitative results from the combined Voyager crossings was the confirmation of interstellar plasma density. From Voyager 1's plasma wave oscillation measurements and Voyager 2's direct plasma science measurements, the electron density in the local interstellar medium was determined to be in the range of roughly 0.08 of an electron per cubic centimeter, about 40 times denser than the plasma inside the heliosphere at those distances. This density is physically important because it sets the pressure the interstellar medium exerts on the heliosphere. Higher density means higher thermal pressure, which means the heliosphere must maintain higher solar wind pressure to remain in equilibrium, which means the boundaries are pushed closer to the star. The higher than expected density was one piece of the explanation for why the boundaries were found at somewhat shorter distances than many models had predicted. Though, as with everything in outer heliosphere physics, the full picture involves multiple interacting factors. The combined measurements from both heliopause crossings also constrained the interstellar magnetic field direction. The field just outside the heliopause was oriented in a way that matched, with some refinements, what had been inferred from earlier observations of interstellar dust polarization and from the energetic neutral atom maps provided by the Interstellar Boundary Explorer satellite. The interstellar magnetic field in the solar system's immediate neighborhood makes a relatively small angle with the galactic plane, roughly threading through the local interstellar cloud along a direction that is tilted only modestly from the plane in which the galaxy's stars predominantly orbit. Knowing this direction with precision matters for modeling the heliosphere's shape and for understanding how galactic cosmic rays reach the inner solar system. What both spacecraft were now sampling, a few astronomical units outside the heliopause, was not the undisturbed interstellar medium at large. It was the very local interstellar medium immediately adjacent to the heliosphere, a region where the heliosphere's presence has disrupted and modified the local gas and field over billions of years. The heliosphere presses outward against the surrounding interstellar medium, and the interstellar medium presses back, and in the region just outside the heliopause, this interaction creates conditions somewhat different from what would exist far from any stellar system. The plasma there may be hotter and more compressed than in the undisturbed interstellar medium farther away. The magnetic field may be draped and organized by the heliosphere's presence in ways that would not exist in open interstellar space. To fully characterize the interstellar medium that the solar system is truly embedded in, measurements farther from the heliopause would be needed, farther out than either Voyager can currently reach with remaining power. The data from both crossings has also provided the first direct measurements of the galactic cosmic ray spectrum in the immediate interstellar neighborhood. Galactic cosmic rays are high-energy charged particles, mostly protons and heavier atomic nuclei, accelerated by violent processes throughout the galaxy, including supernova explosions and their remnants, the powerful winds of massive stars, and possibly jets from compact objects. They travel through the galaxy at near the speed of light, diffusing through the galactic magnetic field in a random walk that takes millions of years before they eventually escape the galaxy or lose their energy. When they arrive at the solar system, they encounter the heliosphere, which acts as a partial shield. The heliospheric magnetic field, carried outward by the solar wind and organized into a spiral structure, scatters and deflects the lower energy cosmic rays, preventing them from penetrating all the way to the inner solar system. The heliosphere is not a perfect shield, and at high enough energies, the cosmic rays pass through largely unhindered. But at energies in the range of a few 100 million to a few billion electron volts, the heliosphere significantly reduces the cosmic ray flux reaching Earth and the other inner planets. Outside the heliopause, Voyager 1 measured the full, unshielded cosmic ray spectrum. The intensity was roughly 4 times higher than at Earth's orbit, even accounting for the difference in the shielding efficiency at different positions. The spectral shape, the way intensity varies with particle energy, matched theoretical predictions for cosmic rays originating from supernova remnants and diffusing through the galaxy's magnetic field, providing confirmation that the basic model of galactic cosmic ray origin and propagation was broadly correct. At the very lowest energies accessible to Voyager's instruments, the cosmic ray spectrum showed features that carried information about how far from the heliopause the measurements were made. Because the heliopause modifies the cosmic ray spectrum at low energies in ways that depend on the boundary's properties. These spectral fingerprints provided additional constraints on the heliopause's characteristics that complemented the direct magnetic field and plasma measurements. The galactic cosmic ray intensity measured outside the heliopause has implications that extend well beyond fundamental physics. Galactic cosmic rays reaching Earth produce secondary particles that interact with the atmosphere, generating carbon, 1,4, and other cosmogenic isotopes incorporated into living things and sediments. Geologists and archaeologists use these isotopes to date ancient events. The cosmic ray flux reaching Earth has varied over geological time as the solar system moved through different regions of the galaxy, encountering denser or more turbulent interstellar material, and as the solar wind varied over the solar activity cycle. The Voyager measurements of the full, unshielded cosmic ray environment now provide the baseline against which historical variations in cosmic ray flux at Earth can be assessed. That baseline is relevant for understanding how Earth's cosmic ray environment has changed over billions of years, and possibly for understanding how those changes might have influenced mutation rates and the pace of biological evolution. Cosmic rays reaching Earth's surface also contribute a small but measurable radiation dose to every living thing. Understanding the heliosphere's shielding efficiency and how it varies is part of the broader picture of Earth's radiation environment that matters for both biology and long-duration human spaceflight. The two heliopause crossings, Voyager 1 in 2012 and Voyager 2 in 2018, provided a kind of triangulation on the heliosphere's outer boundary. By measuring the boundary distance, the plasma properties, and the magnetic field at two separate points separated by tens of astronomical units and located in different directions from the center of the solar system, scientists gained their first actual observational constraints on the three-dimensional geometry of the heliosphere's outer surface. The results confirmed the asymmetry and added specific numbers to what had previously been theoretical estimates. But 2 points do not define a surface. The vast majority of the heliopause, the flanks, the tail, the polar regions, the parts facing away from both spacecraft, remained unmeasured. The heliosphere's shape as a whole was still largely inferred from the 2 data points and from the energetic neutral atom maps that the Interstellar Boundary Explorer provided from near Earth. The energetic neutral atom maps from the Interstellar Boundary Explorer had been available since 2009 and had already changed the picture of the heliosphere significantly before the heliopause crossings occurred. Those maps showed the boundary region not as a smooth, uniform surface, but as a complex, structured environment, with variations in emission intensity around the sky that reflected variations in the underlying plasma and field conditions. The brightest features in the maps corresponded to regions where the heliosheath plasma was hottest and densest, the locations where the solar wind was most strongly shocked and compressed against the outer boundary. The pattern was consistent with the overall picture of an asymmetric heliosphere, compressed from certain directions and more expansive in others. But the maps also showed the ribbon, the anomalous feature that nobody had predicted, running as a bright arc across the sky, in a band that corresponded to the circle on the sky, where the interstellar magnetic field was perpendicular to the line of sight from Earth. The ribbon's brightness varied around its length, faded and brightened with the 11-year solar cycle, and showed time evolution that provided information about the timescales of the physical processes creating it. Each new map from the Interstellar Boundary Explorer added to the picture of a heliospheric boundary shaped by the strong, organized interstellar magnetic field outside it. Together, The in-situ measurements from the Voyagers and the remote sensing maps from the Interstellar Boundary Explorer were telling a coherent story, even if many of its details remained unresolved. The solar system sits inside a magnetic bubble, the heliosphere, whose shape is determined by the competition between the outward pressure of the solar wind and the inward pressure of the interstellar medium. The interstellar medium in the solar system's neighborhood is warmer and denser and more strongly magnetized than the models built before any of these measurements had assumed. The interstellar magnetic field is organized along a specific direction that shapes the heliosphere asymmetrically, compressing it more strongly in some directions, modifying the flow of the solar wind within the heliosheath, and creating the energetic neutral atom ribbon that encircles the sky along the magnetic field's orientation. The heliopause is a sharp, well-defined surface rather than a gradual transition zone. The heliosheath inside it is a complex, turbulent environment where energy budgets do not balance, and particle acceleration mechanisms are not where the theories place them. The magnetic highway allows particles to cross the heliopause in both directions through connected field lines. And beyond the heliopause, the interstellar medium in the solar system's immediate neighborhood is a warm, partially ionized plasma, with its own dynamics and structure, different in important ways from the average interstellar medium on large scales. This picture replaced a simpler, cleaner picture that had been the standard for decades. The old picture had the heliosphere as a smooth comet-shaped bubble with a clear, distinct inner structure and a gradual outer transition into a quiet, cold, neutral, interstellar medium. The new picture was of a dynamic, asymmetric, magnetically complex structure embedded in a warm, magnetized, structured interstellar environment that actively shapes it. The transition between the two pictures required every prediction to be checked and every assumption to be examined. And that process of checking and examining was driven almost entirely by the data the Voyagers sent back across billions of miles of space over the course of decades. Each finding that contradicted the models generated new theoretical work, which generated new predictions, which in some cases could be checked against existing Voyager data, and in others would have to wait for future missions. The iterative process of prediction and measurement and revision is exactly how scientific knowledge is supposed to advance, and the Voyager mission provided some of the most important data inputs to that process in the history of planetary and heliospheric science. Both spacecraft continued operating in interstellar space after their heliopause crossings. Power continued to decline on both, instruments continued to be shut down one by one, and the science teams continued to manage ever tighter power budgets to keep the most essential measurements running. The plasma wave instrument, the magnetic field instrument, and the cosmic ray instruments were the highest priority to maintain. Each year that the spacecraft continued to transmit extended humanity's first direct measurements of the interstellar medium to a slightly greater distance from the heliopause, building a longer baseline along the two spacecraft's respective directions of travel. The data from those continued measurements would eventually provide the first direct evidence of how the interstellar medium varies with distance from the heliopause, whether the immediately adjacent region is significantly modified by the heliosphere's presence compared to the undisturbed interstellar medium farther away, and over what length scale any such modification fades. That information would not be available from any other source. The Voyagers were the only instruments in a position to provide it, and they were slowly running out of time. While the Voyagers were pressing outward through the heliosheath, a separate mission was building a global picture of the boundary region from close to home. In October 2008, NASA launched a satellite called the Interstellar Boundary Explorer into an orbit that took it well beyond the Moon but kept it in the inner solar system, close enough to Earth that scientists could download its data quickly and regularly. This spacecraft's purpose was not to travel to the edge of the solar system, but to see the entire boundary region at once, the way a person standing on a hill can see the entire shoreline of a bay rather than just the small stretch of sand immediately underfoot. It accomplished this by detecting particles called energetic neutral atoms, and the technique it used turned out to be far more powerful than anyone fully expected when the mission was designed. Energetic neutral atoms are created in the outer heliosphere through a process called charge exchange. Solar wind protons streaming outward encounter neutral hydrogen atoms that have drifted inward from the interstellar medium. Hydrogen atoms carry no charge and are not deflected by the heliospheric magnetic field, so they drift inward freely. When a fast-moving solar wind proton gets close enough to a slow-moving neutral hydrogen atom, the proton captures the atom's electron, neutralizing itself and leaving behind a new, slower proton. The newly neutralized particle, now an energetic hydrogen atom rather than a proton, continues traveling in the direction it was moving at the moment of the exchange, in a perfectly straight line, unaffected by any magnetic field. It can cross the entire solar system in a straight line from the outer heliosphere all the way back to the inner solar system. If its trajectory brings it toward Earth, the interstellar boundary explorer can catch it, measure its energy, and record the direction it came from. By doing this for millions of particles from every direction in the sky, the spacecraft assembled a map of the heliospheric boundary, an all-sky image showing where energetic neutral atoms were being produced most abundantly, and therefore where the heliosheath plasma was hottest and densest. The first complete sky map was published in October 2009. It was immediately striking. The map showed broad, diffuse emission from the direction of the heliosphere's nose, the region facing the interstellar wind, as expected. It showed fainter emission from other directions, also broadly expected. But running across the entire sky, in an arc roughly 15 to 20 degrees wide, was a band of intensely bright emission that had not appeared in any prediction. The band was visible in every energy range the spacecraft could measure. It cut across the sky in a great circle that bore no relationship to the plane of the solar system or to the direction of the interstellar wind. It was bright enough and organized enough and unexpected enough that the science team initially doubted their own data. They checked the instruments. They verified the calibrations. They looked for artifacts that could explain a feature of that brightness and that geometry. There were none. The band was real, nothing like it had been predicted. The band came to be called the ribbon. Its discovery prompted an immediate outpouring of theoretical work aimed at explaining what could produce a bright, organized arc of energetic neutral atom emission encircling the sky. The key clue was geometric. When scientists plotted the ribbon against maps of other heliospheric and interstellar properties, they found that the ribbon lay along the great circle on the sky, where the local interstellar magnetic field was perpendicular to the line of sight from Earth. This was not a coincidence. A geometric constraint requiring perpendicular interstellar field orientation was the hallmark of a specific physical mechanism, the secondary neutral process. In the secondary neutral picture, solar wind protons escape through the heliopause into the interstellar medium, where they travel a short distance before undergoing charge exchange and becoming energetic neutral atoms. Those neutral atoms travel a bit farther, then are reionized by the interstellar radiation field or by charge exchange with interstellar protons, becoming slow protons again. The slow protons then gyrate around the local interstellar magnetic field lines in tight circles. As they gyrate, they eventually undergo another charge exchange and become neutral atoms again, flying off in whatever direction they were moving at the moment of the second exchange. The crucial insight is that these gyrating protons will be aimed back toward the inner solar system most effectively when the magnetic field they are gyrating around is perpendicular to the line from Earth to the region where the gyration is happening. This geometric condition concentrates the flux of particles aimed toward Earth in a band on the sky, the ribbon. The band's position tells you the direction of the interstellar magnetic field. Its intensity tells you something about the solar wind's properties at the heliopause in different directions. Its time variation, correlated with the solar activity cycle, tells you about the transport time of solar wind protons from the heliopause to the region where they are being processed and returned. The ribbon's existence had a profound implication for our understanding of the heliosphere's relationship with its surrounding environment. For the secondary neutral mechanism to work as described, the local interstellar magnetic field had to be sufficiently strong and well organized to confine gyrating protons on circular paths of the required radius. Weaker fields, or more turbulent fields, would scatter the protons instead of focusing them into the narrow ribbon geometry. The fact that the ribbon was narrow and bright meant the interstellar magnetic field near the solar system was organized and stronger and more coherent than most pre-mission models had assumed. This directly supported what the Voyager termination shock and heliopause crossings were also showing. The interstellar environment around the solar system was more magnetically active and more structured than the simple background medium the models had depicted. The heliosphere was being shaped by a significant external magnetic force. Understanding the ribbon meant understanding how that force operated. The ribbon finding forced a reassessment of the heliosphere's shape. The traditional picture, present in textbooks and review articles for decades, showed the heliosphere as a comet-shaped structure. The nose of the heliosphere, pressed forward in the direction the solar system is moving through the interstellar medium, was depicted as a rounded, blunt shape. Behind it, in the direction the solar system was moving away from, a long tail called the heliotail stretched out for enormous distances where the solar wind would flow outward for a very long time, before eventually mixing with the interstellar medium. The heliosphere in this picture looked like a teardrop or like a comet's head and tail, aerodynamically shaped by the flow of the interstellar wind past it. The new data challenged this picture from multiple directions. If the interstellar magnetic field is strong enough to produce the ribbon, it is strong enough to significantly resist the heliosphere's expansion in directions perpendicular to the field lines, while having a different effect in directions along the field lines. A strong field presses back with magnetic pressure and magnetic tension in a way that modifies the heliosphere's shape differently in different directions, acting on the flanks and tail as much as on the nose that the interstellar wind pushes directly. Some theoretical work suggested that the heliosphere might be rounder than the comet model, perhaps even roughly spherical in overall character, with the tail being much shorter or differently organized than the classic picture. Other models found that the tail might be organized into two lobes rather than a single streaming structure, with the solar wind flowing along the heliospheric current sheet into two opposite-pointing lobes, rather than fanning out symmetrically behind the solar system. This lobe structure was described by some researchers as resembling a croissant when viewed in cross-section. The debate between the comet model, the rounder model, and the two-lobe model has not been settled. No spacecraft has measured the tail region, and the energetic neutral atom maps show emission from that direction, but interpreting it unambiguously in terms of a three-dimensional tail shape requires assumptions about the physics that are themselves uncertain. The IMAP mission, launched in May 2024, will provide much more detailed energetic neutral atom maps that should help distinguish between the competing models. The asymmetry found in the Voyager crossing distances added another data point to the shape debate. Voyager 1 crossed the termination shock at 94 astronomical units in the northern direction, and Voyager 2 crossed at 84 astronomical units in the southern direction, a 10-unit difference. Voyager 1 crossed the heliopause at 122 astronomical units, and Voyager 2 at 119 astronomical units, a smaller difference at the outer boundary. The termination shock showed more asymmetry than the heliopause. This could reflect the fact that the interstellar wind pressure, which compresses the termination shock differently in different directions, is partially averaged out by the heliosheath dynamics before it reaches the heliopause, smoothing the asymmetry at the outer boundary relative to the inner one. The details of how asymmetry varies between the two boundaries carry information about the heliosheath's dynamics that theorists are still working out. Understanding the heliosphere's shape matters beyond academic interest in ridddle. Solar physics. The heliosphere acts as Earth's outermost radiation shield, and its effectiveness at shielding life on Earth from galactic cosmic rays has changed over the solar system's history and will continue to change in the future. As the solar system moves through different regions of the galaxy, it encounters interstellar environments of varying density, temperature, and magnetic field strength. Denser, more magnetized interstellar clouds would compress the heliosphere, reducing its volume and pushing its boundaries closer to the star, allowing more galactic cosmic rays to penetrate into the inner solar system where they could reach Earth. Periods of reduced heliospheric shielding might coincide with elevated mutation rates and could potentially have influenced the pace of biological evolution. Several researchers have proposed connections between the solar system's passage through the spiral arms of the galaxy, where interstellar density is highest, and major events in Earth's biological and climate history, though the evidence for specific causal connections remains debated, and the quantitative link between heliospheric size and cosmic ray flux at Earth is not precisely established. The solar system is currently embedded in a region of the local interstellar medium called the local interstellar cloud, a warm, partially ionized pocket of gas, roughly 30 light-years across, that the solar system has been traveling through for perhaps 300,000 years. The local interstellar cloud is itself embedded in a much larger structure called the local bubble, a region of extremely hot, tenuous plasma that was carved out by supernova explosions roughly 5 to 10 million years ago and is still expanding slowly. The solar system entered the local bubble from a denser surrounding region and is currently traversing the local interstellar cloud within it. The warm, partially ionized character of the local interstellar cloud is what gives the local interstellar medium its higher-than-expected density and temperature as measured by the Voyagers. Calculations of the solar system's trajectory through the local bubble suggest it may exit the local interstellar cloud within the next 20,000 to 50,000 years. Though the uncertainties in the local interstellar cloud's boundaries and the solar system's precise relative velocity make this estimate rough, when that transition happens, the heliosphere will find itself immersed in the hotter, more tenuous gas of the local bubble, rather than in the denser, cooler local interstellar cloud. The heliosphere might expand significantly. Some models suggest it could swell to 2 or even 3 times its current size. Other models find the transition less dramatic. What is clear is that the heliosphere's current size and character are not permanent features. The solar system has moved through many different interstellar environments over its 4.5 billion year history, and each environment shaped the heliosphere differently. The anomalies the Voyagers found have proven to be durable. The missing energy at the termination shock has not been explained satisfactorily. The anomalous cosmic ray source has not been definitively identified. The stagnation region's dynamics remain incompletely understood. The magnetic field orientation discrepancies require more sophisticated models of the heliosphere's 3-dimensional magnetic structure than exist yet. The thinness and sharpness of the heliopause is not fully explained in terms of the microphysics of plasma boundaries at that scale. The excess heating of the outer heliosheath plasma remains mysterious. Each of these unresolved questions is the starting point for ongoing theoretical work, and each one represents a case where the universe presented measurements that differed systematically from the best predictions, requiring real physics, not minor calibration corrections, to resolve. That is exactly the situation where progress in understanding is most likely to occur, because systematic discrepancies between good predictions and careful measurements point directly at missing physics. The Voyager science team has maintained the spacecraft's operation for nearly 5 decades through a combination of careful engineering, willingness to take calculated risks, and occasional improvisation when systems behaved unexpectedly. In late 2023, Voyager 1 began transmitting unintelligible data, a garbled stream of numbers, rather than the properly formatted telemetry the Deep Space Network was expecting. Engineers spent weeks analyzing the problem from over 15 billion miles away. They eventually determined that one chip in the Flight Data System computer, the computer responsible for packaging science and engineering data before transmission, had developed an error, possibly due to a cosmic ray strike after 47 years of operation. The corrupted memory was holding the code that formatted the outgoing telemetry, which is why the data became unreadable. The fix required identifying the affected code, distributing it across other available memory locations, and sending new instructions that told the computer to execute the code from its new distributed address. The commands to implement this fix traveled for 22 hours to reach the spacecraft. The confirmation that the fix had worked traveled another 22 hours back. When Voyager 1 resumed transmitting properly formatted science data in April 2024, it was the result of some of the most impressive long-distance remote engineering in history. The team had debugged and repaired a computer built with 1970s technology, operating in interstellar space at temperatures for which the hardware was never qualified, using only its radio signal as the interface, from a distance so great that the round-trip communication time exceeded a full day. Both spacecraft were designed with redundant systems and multiple fail-safes, specifically because the designers knew that systems would fail over time and that repairs would need to be performed remotely across enormous distances. The engineers who built those fail-safes in the early 1970s could not have imagined that they would be invoked 5 decades later while the spacecraft were operating in interstellar space. But the careful design decisions made then enabled the improvised repairs that kept the mission running. The institutional knowledge built up over 5 decades of operating these particular spacecraft, the quirks, the calibrations, the workarounds for failed systems, existed only in the accumulated experience of the Voyager mission team and in documents going back to the 1970s. The team has managed the transfer of that knowledge from the original engineers and scientists to subsequent generations, a process of institutional continuity that is itself a remarkable achievement. As of 2024, Voyager 1 is approximately 165 astronomical units from the center of the solar system, about 15.5 billion miles from home. It is moving at roughly 38,000 miles per hour. A signal from Voyager 1 takes more than 22 hours to reach Earth. Voyager 2 is approximately 138 astronomical units away in a different direction, moving somewhat slower. Power on both spacecraft has declined to the point where only a handful of instruments remain operating. The decisions about which instruments to keep and which to shut down have been made carefully by the science team to maximize the scientific return from the remaining power. For Voyager 1, the plasma wave system and the magnetic field instrument are among the highest priorities. For Voyager 2, the plasma science instrument's continued operation provides unique, ongoing measurements of interstellar plasma properties that no other spacecraft can make. Scientists estimate that at least some instruments on each spacecraft may continue returning data into the early 2030s before the power budget finally becomes insufficient to operate any science instrument. When the last instrument goes quiet and the Deep Space Network dishes hear only noise from the directions of the 2 spacecraft, the machines themselves will continue. They will keep moving through interstellar space at their current speeds, following the trajectories set by the planetary flybys and the precise orbital dynamics of the inner solar system, unchanged by any force significant enough to deflect them. Interstellar space is extraordinarily empty. The chances of a collision with any substantial object over the next several million years are astronomically small. The spacecraft will pass through the Oort cloud, the vast, spherical halo of comets surrounding the solar system, at distances of thousands of astronomical units. Over the next several centuries, though they will pass through the sparse outer Oort cloud without encountering any comets, they will approach other star systems over tens of thousands of years, passing within a few light years of several stars without coming anywhere near enough to any of them to be captured or significantly deflected. They will continue moving through the galaxy essentially forever, or until some event that our knowledge of stellar dynamics cannot predict. On each spacecraft, bolted to the bus structure, the golden record waits. Gold is one of the most chemically inert materials known. At the temperatures of interstellar space, it will not corrode. The spacecraft structure around it will eventually be eroded by the slow impact of interstellar dust grains and high-energy cosmic ray nuclei, but the record itself should remain largely intact for enormous periods of time. Whether it will ever be found depends on statistics that cannot be calculated. The density of technological civilizations capable of detecting and retrieving it, the probability of a trajectory that passes near such a civilization, the longevity of such civilizations, and factors that may not fit into our current framework for thinking about life in the universe. The record's designers knew all of this. They sent it anyway. The Voyager mission succeeded beyond every reasonable expectation that existed when it was designed. It visited every giant planet and discovered things at each one that rewrote the relevant textbooks. It stayed operational long enough to reach the termination shock, the heliosheath, and the heliopause, revealing at each boundary that the models were wrong in specific, quantitatively significant ways that required serious revision. It sampled interstellar space for the first time in history. It showed that the heliosphere is asymmetric, dynamically complex, and shaped by a stronger and more organized interstellar magnetic environment than anyone had assumed. It showed that the boundaries of the solar system are sharp rather than gradual, that they are magnetically permeable in both directions, that the energy budget of the outer heliosphere does not balance in the way the models predicted, and that the local interstellar medium is denser and warmer and more structured than the pre-Voyager picture had depicted. Every one of these findings was a correction to human understanding. Every correction was the result of actual measurement replacing theoretical assumption. Every measurement required that two machines built with obsolete technology, running on less electricity than a refrigerator, transmitting signals too weak to run a nightlight, operate continuously for decades across distances that make the word enormous seem inadequate. The two Voyager spacecraft are now the most remote human-made objects in history, by an enormous margin. The next most distant spacecraft, Pioneers 10 and 11, fell silent decades ago and have not transmitted since. New Horizons, which visited Pluto in 2015, is on a trajectory toward interstellar space, but will not approach the heliopause for decades, and its power budget will limit its lifespan. No other spacecraft has been built and launched on a trajectory aimed at the outer boundaries of the solar system. The Voyagers remain the only instruments that have ever directly measured the termination shock, the heliosheath, the heliopause, and the very local interstellar medium. For at least the next decade, and possibly longer, they will remain the only sources of in situ data from these regions. What they have told us about where the solar system ends and interstellar space begins has changed heliospheric physics fundamentally, and along with it, the broader understanding of how the solar system fits into its galactic context. The solar system is not sealed in a simple bubble, isolated from the rest of the galaxy. The heliosphere's boundaries are dynamic, complex, magnetically permeable interfaces between two environments that are in active communication with each other. The galaxy presses against those boundaries with organized magnetic forces strong enough to shape the heliosphere's structure. Galactic cosmic rays flood through the heliosphere's shield, reaching every living thing on every planet in the inner solar system. The interstellar medium immediately outside the heliopause is warmer and denser than expected, a reflection of the solar system's current location in the warm, partially ionized local interstellar cloud. The heliosphere has been different in the past and will be different in the future as the solar system moves through regions of the galaxy with different interstellar properties. It is a structure with a history and a future, not a fixed feature of the permanent cosmic landscape. Two spacecraft, launched in the same summer that the first personal computers were going on sale, built by teams of engineers who did their calculations by hand and on early mainframes, powered by decay heat from elements forged in ancient stellar explosions, are now drifting through the space between the stars. They are sending back numbers. The numbers are telling us where we live. And what we have learned from those numbers is that where we live is stranger, more dynamic, and more connected to the rest of the universe than we knew before we sent something out there to look. The science community's response to the Voyager findings has been a sustained, productive argument that continues today. When the anomalous cosmic ray source was found to be somewhere other than the termination shock nose, papers appeared within months, proposing alternative acceleration sites and alternative transport models. When the termination shock was found to be 10 degrees hotter on one crossing than the other, theorists built models of how the shock's properties could vary with direction due to the asymmetric interstellar pressure. When the heliopause was found to be sharp and thin, physicists examined the stability conditions for a plasma boundary between two different environments and asked what physical processes could maintain that sharpness against the diffusion and mixing that would otherwise blur it. When the stagnation region appeared in the data and the magnetic highway was identified, theorists developed models of magnetic reconnection at the outer heliosphere that had to account for the specific conditions there, far from the star, in a low-density plasma, with the particular magnetic geometries the Voyager measurements revealed. The discipline of heliospheric physics was a relatively small field before the Voyager outer heliosphere measurements became the central topic. The termination shock crossing in 2004 brought it to international attention. The heliopause crossings in 2012 and 2018 brought it to public attention, with announcements that carried genuine news value. Humanity's first machines had left the solar system. The combination of public interest and scientific importance generated significant funding for new theoretical work, new computer simulations of the outer heliosphere, and the planning and eventual construction of the successor missions that Voyager's discoveries had made necessary. The Interstellar Boundary Explorer was already flying by the time Voyager 1 crossed the heliopause, and its ribbon discovery had already prompted a reassessment of the heliosphere's shape. The Interstellar Mapping and Acceleration Probe, approved for development in the early 2010s, represented the scientific community's judgment that the questions raised by Voyager required a dedicated, modern instrument for their investigation. These missions were the direct intellectual offspring of the anomalies the Voyagers found. The Interstellar Mapping and Acceleration Probe launched in May 2024 with significantly more capable energetic neutral atom detectors than the Interstellar Boundary Explorer carried. Its maps will have higher angular resolution, better energy resolution, and better sensitivity, allowing scientists to see finer structure in the heliospheric boundary region than the previous mission could reveal. The improved maps should help distinguish between the different models of the heliosphere's shape, particularly regarding the heliotail, whose structure is among the most contested aspects of the current picture. The new mission will also study particle acceleration processes in the inner solar system with instruments designed to address the anomalous cosmic ray acceleration question from a different angle. By characterizing the pickup ions that are the raw material for anomalous cosmic ray acceleration, scientists can better constrain where and how efficiently the acceleration is happening. The combination of the new maps and the new particle data should provide significant constraints on the models, though whether those constraints will resolve the outstanding questions or reveal new ones is, as always, a matter for the data to decide. Further into the future, proposals for a dedicated interstellar probe have been developed in detail. The most prominent proposal, developed by scientists at Johns Hopkins Applied Physics Laboratory in collaboration with a broad community of researchers, envisions a spacecraft launched on a trajectory aimed specifically at crossing the heliopause and measuring the very local interstellar medium with modern instruments designed explicitly for that purpose. Such a spacecraft would carry particle detectors, plasma instruments, magnetic field sensors, and neutral atom cameras significantly more capable than what the Voyagers carry, and it would be aimed at crossing the heliopause in a direction of scientific interest, possibly through the heliotail or in a direction that would complement the Voyager crossing directions. Getting there quickly enough to return data before the instrument's lifetimes expire would require a much faster trajectory than the Voyagers achieved. Various propulsion approaches have been proposed, including a close pass near the star to use solar gravity for extreme speed increases. Though the technical and thermal challenges of such a trajectory are substantial, the scientific case for such a mission has been built directly on what the Voyager data revealed about how much remains unknown, and the mission concept has received serious attention in NASA's long-range planning documents. The legacy of the Voyager mission extends well beyond heliospheric physics. The planetary flybys during the first 12 years of the mission produced scientific results that are still being mined today. The detailed images of Jupiter's moons, Saturn's rings, Uranus's moons, and Neptune's moon Triton remain the highest resolution close-up views ever obtained of many of those objects. The discovery of active volcanism on Io changed the understanding of tidal heating and opened the question of how common internally heated moons might be throughout the solar system and the galaxy. The characterization of Saturn's ring system provided a model system for studying planetary ring dynamics that influences the interpretation of ring systems around exoplanets discovered by transit photometry. The discovery of geysers on Triton helped motivate the search for active geological processes on other cold outer solar system bodies, a search that has been rewarded by the discovery of active geysers on Saturn's moon Enceladus by the Cassini spacecraft, and tentative evidence for active geology on multiple other moons. The Voyager mission's scientific return, measured in the number of fields of planetary and space science it transformed, and in the volume of scientific papers it generated and continues to generate, is among the highest of any space mission in history. The mission has also had a cultural significance that is difficult to fully quantify. The golden records attached to both spacecraft have become cultural symbols in their own right, representations of the human impulse to communicate, to reach outward, to leave a mark beyond the span of any individual life or civilization. They have been written about in poetry and fiction, referenced in music and art, analyzed by linguists and anthropologists, and debated by philosophers. Carl Sagan, who was central to the design of the records and to the broader public communication of the Voyager mission, used the mission as a platform for conveying to general audiences the scale of the cosmos and the significance of the human position within it. His description of Earth as a pale blue dot, inspired by an image taken by Voyager 1 from about 3.5 billion miles away, has become one of the most widely quoted passages about Earth's place in the universe. That photograph, taken in 1990 at the Voyager team's request as the spacecraft was heading outward toward the outer heliosphere, showed Earth as a tiny point of light, barely distinguishable from scattered starlight in the camera's field of view, a mote of dust suspended in a beam of starlight. To use Sagan's description, the image and the words have circulated continuously for 3 decades as a statement about perspective, fragility, and the shared home that all human concerns are conducted upon. The Voyager mission is now in its final scientific years. Both spacecraft are still transmitting. Both are still in interstellar space. Both are still sending back numbers. The numbers describe a boundary region and an interstellar environment that no human instrument had ever sampled before these two machines got there. And what those numbers have revealed has changed in specific and important ways. The human understanding of where the solar system sits in the universe and how it is connected to the larger galactic environment. The corrections the Voyagers forced on 50 years of heliospheric theory were not minor refinements. They were fundamental revisions. The interstellar medium is denser and more strongly magnetized than assumed. The heliosphere is asymmetric in specific ways tied to the organized interstellar field outside it. The boundaries are sharper and more magnetically connected than expected. The energy budget at the termination shock does not balance. The cosmic ray acceleration site is not at the nose of the termination shock. The transition to interstellar space is not gradual but abrupt. Each of these findings has consequences that reach beyond heliospheric physics into planetary science, astrobiology, galactic physics, and the understanding of how stellar systems in general interact with their interstellar environments. The two spacecraft will keep moving through interstellar space long after their instruments fall silent. In roughly 40,000 years, Voyager 1 will pass within about 1.5 light-years of a small red dwarf star. In about 300,000 years, it will approach the inner edge of the Oort cloud. In about 40,000 years, Voyager 2 will pass close to another star in the southern sky. Neither spacecraft will come close enough to any of these stars to be captured or significantly deflected. They will continue moving through the stellar neighborhood, following their trajectories, laid down by the gravitational influences of Jupiter and Saturn and Titan back in 1979, and 1980 and 1981. The gold-plated records will still be attached. The engineering data plates showing where they came from will still be mounted on the spacecraft body. Long after the last person who worked on the Voyager mission is gone, long after the languages spoken by the people who built the spacecraft have evolved beyond recognition, long after the civilization that launched them has transformed in ways that cannot be imagined, those two machines will still be there, drifting through the dark between the stars, carrying forward into the galaxy the evidence that once, for a brief moment in its 4-billion-year history, life on a small rocky planet aimed something outward and asked what was out there, and kept listening long enough to hear the answer. The numbers keep arriving. As of early 2025, Voyager 1's signal takes roughly 22.5 hours to travel at the speed of light from the spacecraft to the nearest Deep Space Network dish. The Deep Space Network, the global array of large radio dishes maintained by NASA for deep space communication, operates around the clock, in part to stay in contact with the Voyagers. The dishes that receive Voyager's signal must track its position across the sky with extraordinary precision, pointed accurately enough to collect every photon from a transmitter generating barely 23 watts of radio power, less than a dim nightlight, across a distance of more than 15 billion miles. The signal arrives at the antenna at a power level of about 1/10 of a billionth of a watt. Signal processing technology developed over decades of deep space communication turns that near infinitesimal trickle of energy into understandable data. The data rate from Voyager 1 is currently about 160 bits per second, slower than the earliest dial-up modems, slower than a telegraph, slow enough that a single image from one of the old cameras would take hours to transmit. The science instruments that remain active send back readings in this trickle. And from that trickle, the science team extracts measurements of the magnetic field, the plasma wave environment, and the charged particle populations in interstellar space at a point farther from Earth than anything human has ever been. The whole enterprise, decades of careful operation, improvised repairs across billions of miles, progressively more ambitious science, at a greater and greater remove from the star that produced the civilization that launched the spacecraft, is one of the most sustained achievements in the history of human technology. And it continues.